Hello, my name is Johannes Flemming. I'm a principal scientist at the European Centre for Medium-Range Weather Forecasts that implements the Copernicus Atmosphere Monitoring Service, short CAMS, for the European Commission. We asked our community what they want to know about the Antarctic ozone hole, and I'm happy to answer some of your questions in this video. So what we call the ozone hole is a rapid and annual reoccurring strong reduction in the amount of ozone in the stratospheric ozone layer over Antarctica. So let's start with a brief introduction of the ozone layer. Ozone is a chemical species consisting of 3 oxygen atoms, which is different from normal oxygen, which consists of 2 oxygen atoms. The ozone layer is a layer with high concentrations in the stratosphere everywhere, and it's located about 15 to 30 kilometers above the ground. The ozone layer is very important for any life on Earth because it protects us from harmful ultraviolet radiation coming from the sun. The ozone destruction that we call then the ozone hole is caused by chemical reactions of ozone with chlorine and bromine compounds, mainly over Antarctica. These chemicals mainly originate from a class of chemicals called CFCs. CFCs are very stable compounds which were widely used until the 1990s, for example in refrigerators or in air conditioning. Once released, the CFC travel through the atmosphere into the upper stratosphere where they are broken down and when they form those chlorine and bromine compounds which lead to the destruction of ozone. So the rapid ozone destruction leading to the ozone hole is especially efficient under the conditions we find over Antarctica in winter and spring. There are strong winds and cold temperatures, and they form a strong polar vortex. This vortex isolates the air from inside the vortex and outside. During polar night, the temperatures can drop really low, below 78 degrees, which are the conditions for the formation of polar stratospheric clouds. During the winter, the chlorine compounds accumulate on the PSCs. When then, in August or September, the first sunlight occurs, these are rapidly released from the PSC surfaces and they are converted into chlorine and bromine radicals. Each of these radicals can destroy up to thousands of ozone molecules in chain reactions. This process of the ozone destruction continues then during September and October as long as the vortex remains stable. When the sun warms up the vortex even further, the boundaries become weaker and ozone-rich air from the outside the vortex is mixed in, which then leads to what we call the closure of the ozone hole. The ozone hole was first discovered by British scientists in the early 1980s by analyzing UV radiation observations from the Halley Bay Research Station in Antarctica. They found a strong reduction in ozone that had already started in the 1970s. They published their findings of a strong thinning of the ozone layer in the journal Nature in 1985. The ozone layer absorbs ultraviolet radiation from sunlight. UV radiation is harmful to humans and ecosystems. It can damage DNA, cause skin cancer, cataracts, and also reduces the productivity of ecosystems. You may wonder why an ozone hole over the mainly uninhabited Antarctic matters so much. But there are studies that show damage to phytoplankton and krill in the Antarctic Ocean. The process of rapid ozone destruction involving PSCs and CFCs also occurs over Arctica in spring, but it's less pronounced there because the polar vortex is not as strong. But it's worthwhile to remember that mixing the air from the ozone hole, which has reduced amounts of ozone, also affects the ozone layer everywhere. And the processes of CFC introduced reduction of ozone also has an impact globally. The ozone layer, or more correctly the atmospheric ozone column, can be measured from the ground with radiometers which determine how much UV light from the sun reaches the ground. These measurements were already carried out in the 1920s. They are still there and they are very precise, but they only measure the ozone layer at a given point during daytime. Since about the 1950s, balloons equipped with ozone concentration measurement devices were used to not just observe the total column, but also the vertical structure of the ozone concentrations. There is now a worldwide network of ozone zones, and there are several ozone zone stations in Antarctica. Since the 1970s, satellites have been used to observe the total column of ozone. They provide a much better spatial picture of the extent of the ozone loss in the ozone hole. Well, it's still the CFCs and other ozone-depleting substances that are controlled and banned by the Montreal Protocol now that have an impact today. These substances have atmospheric lifetimes of up to 100 years and they remain in the stratosphere for a very long time. The emissions are now much reduced, but there are still some emissions, for example from old cooling devices or from factories that produce alternatives for the CFCs. It's clear from the observations that the continuous increase of CFCs has stopped and that the concentrations start now to go down. There is concern that CFCs and similar species, the HFCs, contribute also to global warming. So it's important that not just ozone, but all the other chemical trace gases contributing to the ozone loss are carefully monitored and observed. In CAMS, we have recently upgraded our modeling system to not just provide information about stratospheric ozone, but also to simulate chemical species involved in the process. But it's not just human-made substances that have an impact on the depth of the ozone layer. It is estimated that about 10% of the chlorine content in the stratosphere is from natural sources, such as volcanoes or vegetation, ocean and wildfire. Also, sulfate aerosols injected during volcanic eruptions could support the ozone depletion process. But the natural sources have only a small impact and only limited over very shorter timescales. So they are not responsible for those long-term ozone trends. The ozone hole still occurs every year over Antarctica. Model simulations predict the disappearance of the ozone hole phenomena over Antarctica for about 2060. So have a look at the CAMS monitoring pages for the ozone hole for more details. And these were all your questions. Many thanks. If you want to learn more about the ozone hole, we have dedicated pages on Atmosphere Copernicus AU where you can follow the latest developments and get all the data for free. Don't forget to follow us on YouTube, Blue Sky and Instagram, and see you soon.